Hello, my name is Ghazal Rezaee and this video is a presentation of my Biomechatronics Systems course final project at KNTU University of Tehran, Iran. The project is about a driving assistant device which could detect a driver's drowsiness based on their brain signals and act accordingly. This project is just a basic offline demonstration on how the device would work. The actual model should have much more sophisticated algorithms and systems. So for this project, I've utilized MATLAB Simulink and Simscape as the main platform. Driver fatigue is a mental concern that weakens the driver's ability to control the vehicle. It not only poses an injury and fatality risk to the driver, but also to other road users, such as other drivers and pedestrians. 20% of all road accidents are fatigue related. According to World Health Organization, more than 1.3 million people are killed in traffic accidents every year due to driver fatigue. Hence, by designing a driver fatigue detection device, we hope to reduce the number of accidents due to this phenomenon per year and help save as many lives as we can. The device contains an EEG headset which measures and sends brain signals to the processing systems attached to it. The processing unit, which its main purpose is detecting drowsiness, uses the EEG signal to determine whether the driver is drowsy or not. Then, depending on the given result, it enables the control algorithm. This is a two-class classification, meaning we are only able to distinguish whether the driver is drowsy or not, meaning we cannot measure knowing between states. The control algorithm is to activate a horn with a distinguishable sound, which could alert the driver themselves and also other road users. As I said, this is a simple and primary model, and the real device should have multiple control algorithms depending on the severity of the situation. The current methods for driver fatigue detection could either be psychological, video-based, or physiological. Psychology-based approach relies on psychometric questionnaires to evaluate the individual's fatigue level. A video-based approach usually monitors the behavioral and physical status of the driver, such as facial features and head position. Physiology-based approaches use biosignals associated with driver fatigue, such as EOG, which is the measurement of the movement of the eye, EEG, which detects uh, the brain states, ECG, which detects heart rate, and EMG, which measures muscle activity. Psychological measurement is time-consuming and subjective since it relies on the driver's subjective feedback via questionnaires, which makes it infeasible and unreliable for real-time detection. Video-based approaches are vulnerable to environmental factors such as brightness, weather, road conditions, and other factors which could result in poor detection performance. Each biological signal has its advantages and disadvantages. Among them, EEG has a good potential due to its high temporal resolution, high portability, and good sensitivity. This project is subcategorized in two parts. First, signal processing and detection using MATLAB coding and EEG lab, and then simulation in MATLAB Simulink and Simscape. To show the demonstration of the processing unit, I've used machine learning methods. The steps are data uploading, signal processing and pre-processing, feature extraction, feature selection, classification, performance and estimation, and control. I'll explain each step in more detail later. The data is the original EEG data of 12 healthy subjects in each state. The files were created by a 40-channel neuroscan amplifier. The sampling frequency is 1 kHz and the duration of each trial is 300 seconds. First, we need to pre-process the signal because the quality of the data and the useful information derived from it directly affect the ability of our model to learn. These steps contain uploading the data via EGLab commands, removing bad channels, applying notch filter, applying high-pass and low-pass filters of half Hz and 50 Hz, and removing the baseline. In this project, I have not epoxed the signal. Epoxing the signal is recommended since it improves the performance of the device. The next step is feature extraction. Based on the literature on this subject, the features I've chosen are two types of entropy. Entropy of log energy and entropy of Shannon. These features are extracted in three domains: time domain, frequency domain, and time frequency domain. For the latter, I resampled the data to 960 Hz. The classification is carried out using each domain feature separately and once by selecting the best features among all. The classification is carried out by four types of classifiers. The first one is KNN. In this method, the classifier finds a certain number of neighboring data. Let's say, for example, 5. Depending on which class the majority of them belong to, it categorizes the new data as the same class. For instance, if 3 of our neighboring data belong to class A, 1 to class B, and 1 to class D, the classifier categorizes the data as a class A. The second classifier I've used is SVM. SVM maps training examples to point in space so as to maximize the width of the gap between the two categories. New examples are then mapped into that same space and predicted to belong to a category based on which side of the gap they fall. The third classifier is the tree classifier. In this tree structure, leaves represent class labels and branches represent conjunctions of features that lead to those class labels. The last classifier I've used is LDA, which is a dimensionality reduction technique. The goal of LDA is to project the features in higher dimensional space into a lower dimensional space in order to avoid the curse of dimensionality and also reduce resources and dimensional costs. The performance of the machine is measured by accuracy. There are many validation methods such as holdout method, k-fold cross-validation method, leave-one-out method, and random subsampling. Here, I've only used k-fold cross-validation. In order to train the machine, we need to divide our data to two parts: the test data and the trained data. So that after training the machine by the trained data, we use the test data to see what percentage of it is predicted correctly. With k-fold validation, our data is randomly partitioned into k equal sized subsamples. Of the k subsamples, a single subsample is retained as the validation data for testing, and the remaining subsamples are used as training data. The cross-validation process is then reported k times, which each of the k subsamples used exactly once as the validation data. Then the k results can be averaged to produce a single estimation. For feature selection, we need to know what the definition of good features are. Good features are informative, discriminative, and they have no redundancy. Feature selection is done on the features of all three domains. The mechanisms used to select features are divided in two categories: filter methods and wrapper methods, or as we can say, scalar methods or vector methods. Filter-based feature selection methods, such as t-test and ANOVA, used statistical measures to score the correlation or dependence between input variables that can be filtered to choose the most relevant feature. These methods are fast but do not consider the classifier type, so they could result in the less improvement of the result. Wrapper feature selection methods create many models with different subsets of input features and select those features that result in the best performing model according to the accuracy. SFFS or sequential fast forward selection is one of the wrapper methods I've used. In this method, at each level, a feature is selected if it results in the best performance. For instance, if we want to select the top N features, at first, the feature that could result in the best performance alone is selected. Then among the combination of this feature and other features, the best performing couple of features is selected. The procedure is repeated until we have our top N features. These are my results in the three domains and at last after the feature selection on the four type of classifiers I've used. As you can see in all the classifiers, feature selection has improved the results. And the best results belongs to LDA after feature selection, which has the 98.5% accuracy. In order to simulate the control algorithm, I've utilized MATLAB Simulink and SimScape. After the device classifies the data, the output signal, which is either 1 or 2, that are our classes, is given to the control system. Here, since I didn't have real-time data, I assume the signal is a kind of step signal where driver is first alert, which equals to number 1, and after some time, he or she gets sleepy, which equals to number 2. Here, I've assumed that the driver gets sleepy after 0.1 seconds. But of course, we know that in the real time, this time is not at all accurate, and the driver could get sleepy after 5 or 10 minutes or even longer. Note that the numbers are the results of the classification. After we create the step signal, we need to convert it so that the SimScape model can interpret it. So as you can see, I've used this converter or link to turn my Simulink signal into SimScape signals. Then the signal is fed to a PS switch. In this switch, if the magnitude of the signal is 2, which means the driver is sleepy, the switch closes. Then the circuit is closed and the voltage is supplied from the battery to the solenoid. And as you can see here, the threshold is 1.1, meaning if the value of our signal is more than 1.1, or as we can say 2, the switch closes. The moment the solenoid's voltage is not 0, it starts to close. Here I've selected the initial distance 10 millimeters. If the solenoid closes, the horn is activated. Since SimScape does not have a buzzer block, I've used Simulink Audio Writer. First, I've used a converter to convert the biomechanical signal to electrical signal so that I can interpret it easier. Then, I've used a voltage sensor to measure the voltage. The signal is then converted to Simulink signal by the PS link, as you can see here. In my control algorithm, I wanted to enable the driver to manually turn off the buzzer so that it indicates he or she is alert. For this, I needed to make the signal constant when it reaches the value of 2. So I use the SR flip-flop to make the signal constant. For the flip-flop to work, I need to turn my voltage to a digital number. So I've used this switch. The voltage here is in the range of 0 to 2, meaning if we have the input 2, we need the input of our SR flip-flop to be 1. The set value should be 0. So here I've used the switch with a threshold of 1.5, which means whenever the signal reaches the value of 2, it passes the constant 1 to the SR flip-flop. And if it is not, it does not pass anything, which equals as a 0 value. Then for the reset, I've used a manual switch, which if pushed, gives the value of 1 to the reset button, and the horn is reset and turns off. Then I've attached the output of the flip-flop to an enabled subsystem. This subsystem is created because I had some issues with audio device writer. This block's input could be only a sine wave, and if I wanted to attach the output signal directly to the input of the audio device writer, it did not make any sound. To solve this problem, I've used two sine waves. I've subtracted one from the other. They're identical. I've used the gate not in here so that when the output is 1, it does not enable this block, which means the original sine wave is fed to the audio device writer and it makes a sound. When the output is 0, meaning the driver is alert, this second sine wave is subtracted from the first one, meaning the signal here equals to 0, which means we can hear no sound. Now I will run this model so that you can see after 0.1 seconds, the audio device writer will make a sound, meaning the driver has become sleepy. You can monitor the time here. As you can see, after 0.1 seconds, the audio device writer makes a sound. Now I want to manually shut the device down. As you can see, after using the manual switch, we can hear no more sound, which means the driver is alert and has switched off the horn. And this concludes my presentation. If you enjoyed this video, please click the red button below to subscribe.